Sungkyunkwan Universities. Today I'll talk about the gap between theory and reality. This means that in real society, myth and misunderstanding about provably secure cryptography are widespread. This means that many people say that many people say that our system is secure because they use provably secure cryptographic algorithms. But we cannot guarantee the whole system's security when we cannot guarantee it is still secure when it is implemented. So in these lectures, I will show you some implementation errors in building secure systems by using cryptographic primitives. My talk is divided into the 5 parts. Firstly, I'll talk about the implementation errors in generating randomness and nonces, and then I'll talk about the smart card and USB systems, and also I'll talk about some implementation errors in handling error messages and adding and in the pattern schemes. And finally, we will talk about some errors in implementation of handshaking protocols, of secure protocols such as SSL and so on. Also the former Secretary of the U.S. Department of Homeland Security, Tom Leach, said about the importance of the secure codings. As you know very well, the generation of random number is very essential to cryptography, such as generating initial vectors for stream ciphers, generating initial vectors for data encryptions, and key streams for stream ciphers, and nonces and patterns and so on. So if the randomness is not generated properly, the whole system can be broken. So we need high-quality pseudo-random number generators. In 1996, Ian Goldberg and Dave Wagner questioned that how the Netscape web browser generated its session keys for secure socket layers. To do this, they reverse engineered the Netscape web browser programs, and then they find the source code of pure ng of Netscape web browsers. This picture shows a C code of pseudo-random number generators of Netscape web browsers. As you can see, this code use time of day and process ID and current process ID as a seed value of pseudo-random number generators. But if the attacker has an account on the same machine as the browsers, he can get the process ID and parent process ID by using the PSE instruction and the TCP dump programs. And then by using exhaustive search, he can also get the information about the microseconds. Then he can reconstruct all the information of the seed, and then he can regenerate the random sequence of the random number generators. This sort is also possible even if the attacker does not have an account on the same machines. After this result was announced, the Netscape web browser is upgraded, and then they use a secure combination of the seed values and public pseudo-random number generator standard. Yes, and then I'll talk about the generating method of nonces. As you know very well, nonce is a number of strings that is never to be repeated over the life of a session. It is used for initialization vectors for data encryptions and counters and so on. Now, our talk, I will show that implementation errors of nonces make the whole system is totally insecure. Wi-Fi network uses radio transmissions, so it is prone to eavesdropping. To prevent these attacks, IEEE makes some standard which is called as a wired equivalent privacy, shortly WEP, in 1999. However, this web protocol was poorly designed, so it has so many secret weaknesses. Among them, repeating nonces, this nonce means initial vectors. Repeating IVs is very common and lead trivial attacks. This is overall structures of web security protocols. As you can see, this is very similar as a one-time path of channel. As you can see, this RC4 encryption is used as key stream generators of a one-time path. This value K is a pre-shared key between two parties, and IV means initial vectors of block ciphers. The key K, this value, the key K is prefixed in advance between two users, so it does not change. And web standard recommend that this value IV should be changed for every sessions. But the problem is that web standard just recommend this. This standard does not require it. So many vendors use initial vectors like this. In PCMCI car, recess initial vectors is equal to 0 on initializations, and then increase this one by one for each packet. So if the initial vector repeats, then this value is also repeats. And like as in the case of the one-time path, if the key stream is repeated more than twice, we can easily decrypt the ciphertext. We can easily decrypt ciphertext by simply exploring two ciphertext like this. Maybe in 2009 or 2008, Professor Seungjoo Kim of Sungkyunkwan University also announced that some secret weakness of wireless LAN-based payment systems of major department stores of Korea. Now let's talk about messengers. Naton is the number one instant messengers in Korea. SK Communications announced that 25 million users are using Naton service in 2008. In Korea, an average of 10 million people use Naton per day. Naton Messenger provides various services, such as a tracking service and single sign-on link between chatting window and the cyber homepage, and remote control, and so on. In 2007, several Korean researchers reverse engineered the Naton programs in order to find the authentication mechanisms of Naton messengers. They find that Naton authentication programs consist of the following components. If user has a Naton email account, then when user types his ID and password, then network messenger send the user's identity informations and the MD5 hash result of the password and ID through the web service. You should note that this MD5 hash functions does not contain any random values, like such as random nonces or random challenges and so on. So these MD5 hash values is some kind of constant values. So we can mount just reply attacks to these network messengers, and we can impersonate some people very easily. To withstand the reply attacks, these MD5 hash functions should contain some random challenges and nonces. This result appeared in the journal dailies. And then, now my third topic is about the way of storing the cryptography keys. Especially I will talk about the smart card and USB tokens. Many cryptographic systems assume that the smart card can carry the cryptographic keys and perform cryptographic operations. This slide shows an internal structure of the smart card. Smart card consists of 8-bit microprocessors and ROM and EEPROMs and RAMs and crypto core processors. This is a logical view of the smart card. You should note that clock signal and voltage signal is provided by using these second and fourth interfaces. And user can input and output their data by using this part. Among the traditional attacks on the smart card, the famous one is the probing attack. To mount a probing attack on a smart card, first we should strip a chip by using the heat and acid liquid like this. Once the chip is open, we can monitor the signals that flows on the smart card bus line by using this. This is called as a microprobe. However, this type of attack is called as a physical attack. Is very expensive because this type of attack needs special equipment and professional knowledge and so on. In 1996, Paul Kosher proposed the sectional attacks, which uses in which attacker gathers informations which is leaked from the outside of the normal cryptographic channels, such as power consumptions and radiations and temperature and so on. After Paul Kosher proposed the timing attacks in 1996, many kinds of sectional attacks are proposed in crypto and Eurocrypt conferences. Let's talk about the power attacks. Many microprocessor-based devices, such as smart cards, consume different amounts of powers depending on the instructions being executed. This is because most of all the small devices, in all the small devices, the dynamic power consumption additionally occurs when the data is switched from the 0 to 1 or 1 to 0. So there is there is a difference in power consumptions. We can use this as additional side information. So it is possible to analyze a secret key which is stored in the smart card by monitoring its power consumptions. Because as I said before, there is a power difference between these two cases and this one. There are two types of power tax. First one is a simple power tax, and the second one is a differential power tax. The first one makes use of characteristics that are directly visible in a single power trace. And the second one looks for side channel differences that are not directly visible in one power measurement. So we should use a statistical method and divide and conquer method. This is a well-known scalar multiplier algorithms usually used for RSA encryptions. This one, E3, E2, E1, E0 is a binary representations of the exponent E. So you should know that when the exponent bit EI is equal to the 0, this algorithm just scalar gen. But this exponent EI is equal to 1. We should additionally perform the multiplication operations. So there is a power difference. This slide shows some power trace on a smart card while RSA is executing. This means that, as I said before, when the exponent bit EI is equal to 1, we need additionally perform multiplication operations. So we can, by using this trace, we can guess hold the secret keys which is stored in the smart card. This trace means scaling, and this means multiplications. Multiplication after the scaling means that the exponent EI bit is equal to 1. The same attack also can be applied to the elliptical crypto systems, like this. Also, the second type of attack is called as a differential power analysis. This is more harder to prevent than the SPA. To mount these attacks, the attacker first chooses an intermediate result of the executed algorithms. This intermediate result must be a function D of some known data and a guessed key K. And then the attacker gets many power traces, and then he gets key values and divide data into two groups by using these guessed keys and the intermediate result function D. And then he calculates mean value curves of each groups in order to remove the noises. And then he get the difference between the averages of these two groups. And then if he can find some spike signals in the difference curve, that means that his guessing is correct. Like this. This is when we can find some spikes in the difference curve, power consumption differential curves. This means that our guessing is correct. But if we cannot find any spikes, then our guessing is incorrect. This is an example of the intermediate result function D. In this case, this is a final exclusible steps of the data encryption standard. Here, the RI is the function of the RI-1 and the KI. It just copied to the RI when the Li-1 is just equal to 0. But if Li-1 is equal to 1, then inversion of this F function is copied to the RI. So there is a difference in power consumptions between the case of Li minus Z is equal to 1 and the case of Li minus Z is equal to 1. So we can use by using this difference in power consumptions, we can guess the whole secret keys stored in the smart card. There is also another kind of assertional attacks which is called fault attacks. This fault attack uses some faulty results of the smart card. This is often applied for breaking RSA mechanisms. Yes, and then move on to the USB flash drives theory. USB flash drive consists of NAND-type flash memory data storage devices integrated with the USB interfaces. As the portable medias, USB flash drives are easily lost or stolen. So several protection mechanisms should be used to prevent the data which is stored on the USB flash drives. Secure USB flash drives usually support the encryption functions and then password authentications and resistance against the reverse engineering and so on. Here we should notice two things. The first one is that every flash memory IC is subject to the light endurance limitations. So after the repeated erase and the program cycles, the memory no longer contains data. So it is very difficult to securely wipe all the sensitive data which is stored in the USB flash memories. And the second thing is that if someone fails to log in more than 3 to 5 times, these secure USB flash memories usually initialize the password, for example 000, and delete all the data stored in the USB memories. SanDisk, Cryptology Micro, and Samsung Formax SPUB, and so on, and LG systems and USB mini slide from LG Electronics use these approaches. By exporting these two things, we can make some attack scenarios. When the attacker steals some others' USB memories, he can intentionally enter the wrong password more than 3 to 5 times. Then USB flash drives will initialize password and delete all the sensitive data stored in the secure areas. But we should note that this data cannot be wiped securely because of the characteristics of the USB flash memories. And then the attacker can recover and access to these deleted data by using any data recovery softwares which can be downloaded from the internet, and then by using the initialized passwords such as 000, and then access to these secret areas and can extract the user private information. Yes, and then I will talk about some implementation errors in the handling error messages. This picture shows some example. This picture shows an example of password login systems. In these login systems, after the user enters his ID, this system kindly displays user ID is whether user ID is a correct one or not. So by using these information, the attacker can build a list of names of the authorized users. So the password system, in the password systems, the failure message should not indicate if it is the username or password that is unacceptable. This is also not correct. This example also gives us some hint about which company system is being accessed before the user enters the correct password and ID. This is the correct one. In these examples, the user is given no information until the system is assured of the ID and password of the users. The system name is displayed after user enters the correct ID and password. Let's see another example. This is a sample C code which implements the password login systems. In these systems, user password is stored in the PW arrays, and this program checks whether the input password and input password is equal to the stored password one by one. Yes, let's imagine that the stored password is 312. Then the attacker first the attacker entered the guessing password 000 to these login systems. Then this password program checks this input password and this input character, and this stored character is equal or not. This character is not equal because this input character, this input is not equal to the stored one. This program will display the error messages. And then attacker inputs the 100. Then this first character is also not equal to the stored password. So this password system displays the error messages. But if the attacker enters the password, guessing password 300, then this input character is equal to this one. So the loop control is moved to the second characters. So we can find some time delays. The case of this and this one. By using these time delays, we can conclude that the first character is 3. By using this divide and conquer method, we can find the whole password only after the 9 steps. Yeah, let's see the more complicated situations. In IP, usually padding is used for increasing length of the messages so that it is a multiple of the block size. This padding can be used for enhancing securities. It can disguise the length of plain text, and it can prevent traffic analysis and so on. However, this padding is very useful in most of the cases, but in some cases, this padding have a negative impact on security. As you know very well, this is a series mode of encryption. Series mode of encryption has a malleability properties. This means that if the attacker flip bits here, Ci-1 block, then it leads to the bit flips in the next block of plain text here. We call this is the malleability of the CIFS mode. By using this property, in 2002, Bodny firstly proposed the padding oracle attacks. In his attack scenarios, first adversary submits CIFS mode ciphertext to the padding oracles, and that oracle decrypts the given ciphertext and checks the correctness of the padding with respect to the particular padding rules. And then also outputs valid or invalid messages according to the correctness of paddings. In P cases number 5, CDC padding rule is defined as follows. This is called as a byte-oriented padding schemes. If we want, if Q bytes are required to fill the last blocks, we should add Q bytes of value Q. This means that if we need 1 byte should be added in the last blocks, we should add 1 byte of value 1. And if we need 2 bytes in order to fill the last block, then we should add 2 bytes of the value 2, like this. Yeah. By using these padding rules and the malleability property of the CIFS mode, we can decrypt the target ciphertext like this. Here the R means the random blocks and CI means the target ciphertext like this. Firstly, adversary gives padding oracles the ciphertext, random cipher block R, and then target ciphertext CI. And then this padding oracle will decrypt these 2 cipher blocks, and then he will compute, he will finally get this region. And then he will check the least significant byte of this one is equal to 1 because of the CIFS padding rules. If the least significant byte is equal to 1, then this padding oracle will give a valid message to the attackers, and then the attacker can finally decrypt the last 8 bytes of the plain text by using these equations. This is a padding oracle task. To protect this kind of attacks, we should use authenticated encryption mechanisms. This kind of attack also can be applied to the RSA systems, which is defined in the P cases number 5 and number 1. Yeah. Lastly, I'll talk about some implementation errors about handshakings in secure protocols, such as secure so-called layers and so on. In general, handshaking means the automated process of negotiation that dynamically sets configuration parameters of communication channels, which is established between 2 parties if a normal communication begins. Handshaking protocols plays a very important role in the authentication and key element process. As you know, SSL means secure socket layer programs. It is originally developed by Netscape incorporations, and also it is IETF standards in as a RFC 246. This SSL program is a very well-known method to make secure channels between web browsers and web servers. These SSL programs consist of 2 sub-protocols. The first one is SSL handshaking protocols, and the second one is SSL network protocols. In SSL handshaking protocols, by using these SSL handshaking protocols, the web server can authenticate himself to the web browsers. And also it allows the server and it allows the browser and the web server to select the cryptologic algorithms and ciphers that they both support. And also by using these SSL handshaking protocols, the two parties can generate shared secret keys by using multi-encryption techniques. Here we should note that two things. The first one is a hello message of the handshaking protocols between the web browsers and the web server is transmitted in a plain text form. And the second one is that web browser software such as Internet Explorer, Firefox, and so on, which uses the SSL protocol, stores the ciphersuit set as a plain text file in the registry directory of MS Windows. This ciphersuit here, the ciphersuit means that ciphersuit is a kind of a list that contains list of encryption algorithms which is supported by web browsers and servers. Yes, in order to attack the SSL programs, first the active attacker. In SSL handshaking protocols, the client web browsers will send some client hello messages to the servers. These client hello messages contains the list of encryption algorithms which can be supported by these web servers. And then this then the attacker can intercept these client hello messages and modify these to this. In this one, the list of encryption algorithms contains strong encryption algorithms. But in these modified ones, these client hello messages only contains weak encryption algorithms such as 40-bit ASCII4 algorithms. And then this server should select encryption algorithms among the weakest ones. In 2009, some researchers proposed another attack which is very similar as a previous attack, this one. This is very similar with the ciphersuit low-level attacks, but it has differences in that this attack, LinkedIn attack, does not intercept any modified client hello messages. Also, it does not modify the ciphersuit configuration files. It just modified the ciphersuit configuration files, which is stored in the client web browser systems. So it cannot be detected by using the message authentication code and so on. In order to mount these attacks to the Internet Explorers, we should know the following things. In MS, for SSL services, MS Windows, Microsoft Windows uses schannel.dll libraries developed by RSN. We can modify this ciphersuit of schannel.dll program by modifying the following registry of Windows, like this. By modifying these registries, we can set the client web browsers uses only the weakest 40-bit ASCII4 algorithms. In order to prevent this kind of attacks, the web server can send this kind of alert message to the web browsers if he receives a ciphersuit which consists of only the weakest encryption algorithms. But as this table shows, very few websites protect their site by using these out messages. This X means that our attack cannot be mounted to the Amazon and AOL auction event, and this all means that our attack can be applied to this site. Yes, I'll talk about some implementation errors in various commercial systems. Here we should know that when we implement some secure systems, we should deal with some implementation aspect and other management errors and so on. I heard that this workshop is mainly participated by the mathematicians. Is that right? Is that right? Yeah. So I want to say that nowadays mathematicians should also know about the programming techniques, especially secure codings and so on. By this, we can minimize some security failures in the commercial security systems. Yes, that's all. If you have questions, I would be glad to answer that at this time.
We have plenty of time.
I think that what you say talk about many attack, such as side channel attack for USB or smart card or SSL. So, what is your answer to resist such a side channel attack or repair such a weakness?
Yes, and first, my main topic is not the side channel attacks. One of my topic is side channel attacks. And to the best of my knowledge, differential power attack cannot be protected theoretically. So, but we can make some protection. We can protect the smart card as hard as I know. But we can make the algorithms that can resist to the some kind of differential power attacks as possible as we can. So when we make a secure coding in smart card and USB and so on, we should follow the some kind of a software engineering method when we develop cryptographic products. We call it as common criteria. Do you know about common criteria? Yes, common criteria is some kind of standard which suggests some developing method of secure commercial products. So if we follow that standard, we can make secure C programs and secure hardware and so on. So, yes, that's all.
Any more questions, please? If there's no more, we'll go to the session. Thanks to the speaker again.